Let's get started. So today we have Nick Battaglia visiting us from Princeton. Nick, as many of you know, was a student here, working with Dick, and then he went to Carnegie Mellon, and now he's at Princeton. He tells us about cross correlation, CMB, cluster.
This is on. The green light means go. Okay, thanks Marcelo for hosting. And I'm going to tell you about many different things about CMB secondaries. And hopefully I'll convince you by the end that there's potential to use them as cosmological probes and also to study cluster astrophysics. This is work done with many collaborators. And also in collaboration with some of the results you'll be seeing from the ACT telescope. So the CMB primary anisotropies have given us sort of the backbone for cosmology. They've nicely constrained things like the sound horizon, the optical depth, the tilt of the power spectrum, the amplitude of fluctuations, all to very, very high precision. And what we know is there's going to be more of these measurements made over the next couple of years. So CMB is constantly going to be observed. The data set's going to get larger and larger. And what we've seen become more and more evident over the past couple of years is that what I call secondaries, some people also call foregrounds, are going to be important. So as an example, the BICEP 2 experiment, it turns out that foregrounds are very important for that measurement. So what can we do with these secondaries? Some people just want to get rid of them. They want to marginalize over them. But they're useful. You can also use them to constrain cosmology and potentially some astrophysics. So what's limiting us right now? Well, like I said, this is a very data-rich field. So we're not data-starved. There's tons of data. It's really a theory-poor sort of field in cosmology, which is nice if you're a theorist. So there's lots to do and lots to play around with. So for those who aren't familiar with CMB secondaries, what happens, or at least one form of CMB secondaries, it's what happens when the photons from our nice uniform CMB backlight transverse across the universe, and they scatter or they're deflected. So when they scatter, it's either thermal, it's known as the thermal or kinetic Syniad-Zeldovich effect. I'll explain those in a second. Or they're deflected by the mass in the space between us and the CMB. And what's neat is that these scatterings or deflections probe interesting epochs in the universe. So early on, when the universe is reionizing, things like the thermal and kinetic, as said, have unique signatures that come from reionization. In the late time universe, these scatterings and deflections and distortions probe the growth of structure in the universe. So it becomes a nice late time probe of the growth of structure, and therefore you can back out cosmological information. Now these secondaries are becoming more and more important because as the CMB measurements have evolved, going from say WMAP down to now ACT and SPT, ACT pole, SPT pole, advanced ACT, SPT 3G, the resolution and the sensitivity of these experiments have gotten much, much better, such that going from WMAP down to Planck, down to say ACT, you start to see these little sources pop out, such as clusters and point sources. And so what this does is when you go and you say take a power spectrum of these maps, these sources become very, very important, and in fact become dominant in your signal. So what I'm showing you here is the power spectrum of the temperature of CMB from low L, about a degree, all the way out to L of 10,000. And what you see as you get around L of 2,000 is all these secondary contributions start to become more and more important, and they even start to dominate once you get past L of 3,000. Now in this region here, I've highlighted this is sort of the sweet spot for the auto spectrum of the thermal SZ and the kinetic SZ power spectrums. This is where you get the most signal compared to either the primary CMB here, or at smaller angular scales, you start getting taken over by the Poisson power from the CIB and radio sources. Yes. So I've mentioned the thermal SZ and the kinetic SZ several times now. For those who don't know, the thermal SZ, you can think of it like inverse Compton scattering. So you have your CMB photon coming into a hot ionized plasma, and that gets upscattered to your observer. And what that does is it distorts the nice thermal black body of the CMB into this spectrum here. So what that means is at frequencies below 217 gigahertz, you see a decrement, and above you see an excess. And this distortion is proportional to the total thermal energy in the cluster. Or if you think of it as a line of sight integration, it's proportional to the line of sight electron pressure. And this is great because it's a nice probe of the thermodynamics of your collapsed systems that you're looking at. The kinetic SE, which I will mention briefly, is you can think of it as like a Doppler shift of your CMB photons, or a moving mirror. So your CMB photons are coming in, and this ionized gas is moving towards or away from you. That will redshift or blue shift your CMB frequency. But this effect is much smaller. It's about an order of magnitude smaller than the thermal SZ. So what are these sources? Well, typically, they're galaxy clusters for the thermal SZ. And that's because this Y parameter, this distortion parameter that I've been talking about, is proportional to mass to the 5/3 if you integrate over area. So more massive things are going to give you a larger distortion compared to less massive things. And galaxy clusters are great because they're nice signposts for the growth of structure in the universe. They're very rare, and they're very sensitive to things like the RMS fluctuations in 8 megaparsecs, also known as sigma 8. This is a particular cluster that we measured in ACT. This is the El Gordo cluster. It is the most massive cluster above a redshift of 0.8 that's been observed. It's a neat merger system with lots of interesting astrophysics going on that you can't really see in this just with these contours. But if you get an X-ray image, you can see actually 2 knots, which is very neat. That kind of sort of highlights the astrophysics of these objects. So what do you do with these, say, clusters that you measure in the SZ or the power spectrum? Well, typically, people go out and they count them. So if you count clusters as a function of redshift, this is, again, sensitive to your cosmological parameters. Or you look at the power spectrum, and the amplitude of the power spectrum that you get is sensitive to, again, your cosmological parameters. So these are sort of the 2 standard ways that you want to use your CMB secondaries as a probe of cosmology. There are other things people can do. You can look at higher order moments. You can look at the PDF. You can look at the bispectrum. You can also just look at the some people like to use this F-gas test. I won't talk about that, but there are many ways you can use clusters for cosmology. In terms of CMB secondaries, these are the 2 sort of main approaches that people use. So what does that look like? Well, when you go out and you count clusters, you're essentially you're integrating over your volume component, and then you have a mass function. But this isn't really a mass function, because when you go out and you measure clusters, say in the SZ, you aren't measuring mass, you're measuring some sort of observable. So you have all your astrophysical assumptions and your modeling go into turning this observable into a mass. So this is where you get your systematics and errors in your number counts. In terms of the TSZ power spectrum, again, you have your volume element, you have your mass function. But you aren't really worried about the proxy. You're worried about what these objects look like on the sky. So this is your pressure profile, the Fourier transform of your pressure profile squared. So this is where your astrophysics come in if you're to use the TSC auto power spectrum. Right. So you have also, when you're counting clusters, you need to know about your selection function. So what clusters are you selecting? Do you know if you have a nice function, a nice mass threshold, or I guess observable threshold, and how that translates again into mass? So this is where all your sort of modeling and systematic errors come into your cosmological constraints. And these are very sensitive to your underlying model of astrophysics that you assume. To illustrate this, I'll show you a plot from a recent cosmology paper, our cluster cosmology paper in ACT. This is showing our constraints on omega m and sigma 8 using ACT cluster counts. And these three contours here just show you three different models for the assumption of the cluster astrophysics. So you can see if we had, and this contour here is from WMAP. So if we knew what the underlying or gastrophysical model, ICM model was, then we'd have a very nice constraint combining with WMAP in this plane. But these models aren't completely crazy, so you kind of think of them as one big large blob, and in that sense we aren't doing that well compared to what the primary CMB has done. So we can go out and we can count more clusters, get more observations of clusters with ACT, but that won't matter. Already we're systematics limited, and SPT is also systematics limited, and anybody who does cluster counts with SZ is systematics limited until you're able to really nail down what the underlying mass proxy relation is, your Y SZ to M relation. And so the goal then is to really try and understand what sort of biases can come in these in this mass proxy relation. What does the scatter look like? Are there correlations between other observables? Anything like that becomes very important in wanting to sort of constrict and tighten up these constraints and reduce your systematics. Simulations are a great tool for doing that, and that's something we've been working on. Also, other observations are a great tool. So things like cross correlations are also a great tool. I mentioned simulations and modeling of the CMB. The reason why it's complicated is there's lots of processes that need to be included. Clusters of galaxies are exactly that, several galaxies together. So you need to form stars in your models. You need to radiatively cool your gas. There's forms of feedback, whether it be AGN, stellar feedback. There's also forms of non-thermal pressure support. These aren't just, they are gravitationally dominated systems, but they're not just gravitationally dominated systems. There's things like kinetic pressure support, cosmic rays, magnetic fields. Clusters are also not spherical. Here's a nice example of a very massive famous cluster. This is the bullet cluster. You can see it's definitely not spherical. The gas is not distributed in a nice round blob. So these are all things that need to go into your model. In simulations, the things in red are things we model currently with subgrid models. And the things in white are processes which we don't need to model. They just come out naturally in your simulations. If you do something like a semi-analytic model, then you need to come up with some sort of model for your asphericity of clusters, how to include kinetic pressure support, things like that. Currently, in our simulations, we don't include things like magnetic fields or any sort of plasma processes. But for what we do, we think these are very subdominant effects and won't really affect the overall thermodynamics of the cluster. So what do our simulations look like compared to observations? So I mentioned the pressure profile was important for the thermal SE power spectrum. So if you don't get that right, you're not going to get your thermal SE power spectrum right. So what I'm showing you here is simulations. This is your pressure profile times R cubed to show you where the total thermal energy peaks. And you can see compared to this dark gray band here, which is low redshift X-ray observations of clusters, we do fairly well to match the results inside the core. Outside the core, these aren't observations. These are just old simulations with crappy subgrid physics in them. So don't worry about this part of the plot. So you can see, compared to this small subsample of X-ray clusters, we do fairly well. If you then go to the current SZ observations of pressure profiles, this is here again is the X-ray profile out to about R over R500, so what some people would call the virial radius. Beyond that, these red points are stacked Planck clusters. This is showing you the pressure profile from Planck as a function of radius. And then our simulations calculated by the Planck team, shown here in brown, and you can see that they actually do a nice job of following the SC data points. This is, again, low redshift, high mass clusters measured by Planck. So it looks like, at least in the simulations we have, we can model pressure profiles of low redshift, high mass clusters.
Is this assuming the universal pressure profile in the Planck analysis?
No, they're just stacking. What they find, though, is an agreement between, what is this, 0.1 and 1 R500 with the universal pressure profile. Beyond that, it differs. And you start to see some deviations out here, but they're small and they're within the errors. That's not saying anything about the core. Remember, a lot of the energy and a lot of the signals coming from out here. And you can go even further. You can look at what do clusters look like at higher redshift. So this is a sample of clusters selected by SPT. And these are X-ray observations where they stacked in two different bins, a low redshift bin, which is about 0.6, and a higher redshift bin, which is about redshift of 1, or no, sorry, 0.47 and 0.8. This is, again, what I showed you earlier. And so this is showing you how two different simulations stack up against the results. And again, they do pretty well, given the errors on the measurements and the errors allowed in the simulations, or the variance in the simulations. So these simulations do well to match the pressure profile, which is what goes into your mass proxy or your TSE power spectrum for high mass clusters at low redshift and high redshift. So what does that mean? Well, it means we can basically make the pressure profile or moderately simulate the pressure profile for high masses. We know what the mass function is, right? Roughly 5%. And we roughly know what the cosmology is, so we can go back to that equation I had for what the TSE power spectrum is, plug it all in, and then go out, and we have these high resolution temperature observations of the CMB. We should be able to match the TSE power from the models and the observations, right? They should be in agreement. Well, these observations do exist, like I said, like I've shown. There's even more recent ones. There's there's ACPOL results that should go on here. There's also SPT George et al. From just a couple weeks ago that should also go on here. But this roughly tells the story of where the observations are. And this is the area we're interested in. You can go, and this is just showing you again the breakdown of the various secondaries that you have to put into your model to extract the TSE signal and the KSE signal. So that's for the high L. You can also do this at low L. You say, how can you do this at low L? Well, experiments like Planck have multi-frequency, have several tons of frequencies, so they can actually remove the primary CMB and go after what your TSE looks like at low L. And that's what they did. So they've made these nice Y maps that aren't public, but they did take power spectrum of them. So this is showing you, forget those arrows. This is showing you the Planck collaboration results from their low L TSE power spectrum. This is showing you what you'd expect given the model and the Planck primary CMB parameters, what the model should be. This is showing you what our model is for concordance cosmology, or concordance cosmology before Planck. And then this gray band is what you'd expect given our model and the Planck cosmology. So Planck cosmology has a higher sigma 8, so that's going to push this up. It also has a higher omega m, pushes it up a little bit. You can see it's kind of in disagreement with their observations here, 1 sigma several times. And then these are the ACT, SPT, Planck constraints at L of 3000. So you can see there's a mild discrepancy. This is, if you look at the recent results from George et al. From SPT, this is a little bit higher, but there's still sort of a, if the Planck primaries are telling you what the story is, then what's going on out here? And we know that this model does really well to reproduce the pressure profile. So where's this power? What's going on here? Why aren't we matching the TSC auto spectrum? So that's sort of the state of where we are. And this has been said in papers as well, right after.
So non-thermal pressure support would do exactly that, right? It would suppress the power at over 3000, right?
But there's non-thermal pressure support in the simulations.
Sure, but they're tuned somewhere, right? So.
No, it's not tuned. It's things falling in, accreting, moving around. It's tuned in, say, if you have an analytic model, you have to try and match it to something.
But there's some AGN feedback parameter.
There's some AGN feedback parameter, but that parameter seems to reproduce a lot of the low redshift, high mass, and even, high mass pressure profiles fairly well.
Is this a 1 sigma or 2 sigma upper limit?
The 2 sigma upper.
That's a 2 sigma.
It's a 2 sigma upper limit. But getting to your point, people have also played around with, say, AGN feedback and what it does to the power spectrum. I mean, we have AGN feedback in our models, but this group here cranked up their AGN feedback to a point where they could sort of get something that looks like, the low L Planck plus ACT and SPT. Now they're still off, by about 2 sigma, but if you start to look at what these mean for the pressure profiles, they don't match any sort of low redshift pressure profile. Their Compton Y distortions look really funky, in my opinion. This blue line here is comparable to what we did in terms of the feedback and what the.
Do you know what redshift contributed most of the points?
Well, so. Yeah, you saw my slides. No, so. We can match the high mass clusters, but a lot of the power at L of 3000, about half the power is coming from low mass, high redshift clusters, which we don't really have constraints on their pressure profile, or any of the gastrophysics that's going on there. So, this is important. This band here is 50%. This is mass, and this is redshift. So, all this area here at L of 3000 is, above it. 50% of the power comes from that region of parameter space, and mass and redshift. So, there's a lot of uncertainty there. We don't have measurements out there. We have predictions from simulations, or if you take some sort of analytic theory, you can say what the pressure profiles look like, but we have no constraints on them currently. So, I guess, the question is, can we do better? This is just an auto spectrum. There are other systematics that can go into the auto spectrum.
This is in the sense that you've got too many hot electrons at high redshift.
That would appear to be the case. The simulations have too much power at L of 3000, so there's too much pressure.
This is tricky, right? Because it's really groups that are contributing a lot of this power. We don't even have good local measurements of it.
Right. Well, 2 times 10 to the 14, you can argue. Yeah. Yeah. Yeah.
Sorry, how low would you have to make sigma 8 for everything to go away?
Not that much lower, but.
So you're believing like sigma 8?
Well, no, I'm saying No.
Well, there's suggestions that if you made tau smaller, that this would change things.
You mean in terms of what Planck is deriving for sigma 8? Yeah, sigma 8 could not be, so this is assuming Planck, this is 0.8, which is what most observations hover around 0.8. The ACT SPT constraints sort of suggest if you just take the TSZ power spectrum, that's more like 0.78, 0.77.
It was very sensitive.
It is very sensitive to sigma 8, yes.
That whole red curve,
Right.
but would it affect the break there?
So this break is basically when you start resolving the clusters. So if you do change the profile to become much, much flatter, then you could get a break earlier. That is possible. But we shouldn't worry too much about the auto spectrum. There are other ways we can get at cosmology. In particular, cross correlations may hold the key to getting at these constraints. So one thing I said was these models do really well at reproducing the low redshift, high mass cluster pressure profile. So one thing we did was we took a bunch of low redshift, high mass clusters and cross-correlated them with the TSZ microwave sky. So here's your microwave sky. It contains SZ, contains CMB, CIB, contains foregrounds, large-scale foregrounds such as dust, synchrotron, also has point sources, and it'll have some noise in it. And then we cross-correlated it with a cluster map. And this cluster map, you consider it like a hits map. Basically, if there's a cluster there, you put a 1. If there's no cluster there, you put a 0. And what this does is it removes a lot of the systematics in your CMB, right? So you can basically, there's no reason why the CMB is going to correlate with cluster positions. There's no reason why the large foregrounds are going to correlate with cluster positions. There's no reason why point sources aren't going to correlate with your cluster positions. Noise shouldn't correlate with your cluster positions.
And CIB, obviously not.
Well, CIB could. It could. In low redshift, in our observations, it does not. And we have a plot of that, and I will show that. But you knew that already. You were on the paper. So here's the catalog that we used. We call it the RBC catalog. It's a subsample of the MCXC, and what this is a X-ray luminosity cut catalog, or so flux cut. So there's a flux limit, and above a certain flux limit, we assume this catalog is complete. There's about 800 clusters. I think in total, we cross-correlated with about 640, made it into the sample after we cut out the plane, the galactic plane.
What was the original sampling?
MCXC.
Yeah, what's that?
It's an amalgamation of many X-ray, X-ray observations around the sky. So we.
Constructed all of the data that are going to give us something to work with.
But these 3 are the only flux-limited surveys. Some of them are serendipitous, so you have no real way to model that. We wanted to come up with a nice sort of selection function, because that's important. If you want to do your cross correlations properly, you need to know your selection function. And Amir can tell you all about how to learn your selection function. But what we did before we learned the selection function was we kind of drew our selection function by hand. Something you should know about the MCXC, all the masses in it, so all these masses here are calibrated from an LXM relation, which has lots of scatter, especially if you don't core X-size your X-ray observations, which you can't because these are all ROSAT, or most of them are from ROSAT. So that means that this, again, this mass proxy relation has about a 20% scatter. And because it assumes hydrostatic equilibrium when they're doing this conversion, there's also a hydrostatic mass bias, which we included. She said it was 20% plus or minus 10%. And then we marginalize over that error. So we take the Planck maps. We also did this with WMAP. And we cross-correlated with our cluster positions. So that's all shown here. And let me just jog your memory. Here's the auto spectrum. right? And this is, again, sensitive to gastrophysics. The cross correlation is only 1 power of your SZ, or sorry, your pressure profile. And then this is your selection function, because you have basically ones, so you have no sort of shape for them, and that shape is beyond the resolution of your cross correlation. So, there is some gastrophysics in here. You really have to understand your selection function and how you're selecting clusters. Is there an uncertainty in that selection function? But you can go out and do this. And what's great about this cross correlation is, again, because we're looking at low redshift and basically very massive clusters, given the RBC selection function, it's very sensitive to sigma 8. It goes like sigma 8 to the 7.4 power and omega m to the 1.9. So we can go into the simulations and do this. Given a selection function, what does that look like? Red is showing you here what it looks like for AGN feedback. You can see if we turn off AGN feedback, actually the cross correlation signal doesn't change very much, which is nice. This is showing that this is pretty insensitive to the sort of cluster astrophysics that you have to assume in, say, an autocorrelation. You can go even more extreme and say the universe doesn't form stars, and you have this shock heating only model, but that's been ruled out already by, we know that there's stars and clusters. But we end up ruling this out at very, very high significance. So what do these cross spectra look like? So this is the Planck. The red points are the cross correlation with the Planck 100 gigahertz map. And this is our best fit model. So given that shape that I showed, we just fit an amplitude. And that amplitude will then, you can translate that into your cosmological parameters. But these amplitudes are very close to 1, which I'll show you. Here's WMAP in the green points. You can see that Planck and WMAP agree, at least in this cross correlation. Here's 143. Again, very nice signal, high signal to noise. This is why I said there's no CIB contamination. At 217, this is the SZ null. You can see that there's nothing here. There's no signal, or no significant signal. And then at 353, you see a nice excess, which is what you expect as well. So this is great. It fits nicely. And you can combine all these measurements to give you sort of like the best fit TSZ cross correlation power spectrum, and that's what we're showing you here in green. This is like our optimally weighted TSZ cross correlation, and this is showing you those Planck points again. You can see that we do much better in our cross correlation than Planck. Now this is an auto spectrum, so we had to arbitrarily scale our points up, but when we did that, we scaled up the error bars as well. But about 2 times smaller error bars than what Planck got for their Compton Y map, which is nice. I will point out that Planck did do something like what we showed here in the green points. So they did take a power spectrum of clusters that they knew about, and they got similar error bars to us, but they did not do a cosmological analysis on them. So this just shows that we get better error bars than what they had on their cosmological analysis, but we're fairly consistent with what they did in their SC catalog. So what do those constraints look like? Just focus on this last line here. This is where we included all the uncertainties, or marginalized over the uncertainties in our selection function. We get about 1% measurements of sigma 8, omega m when you combine them. And then if you marginalize, or if you include information from, say, WMAP or Planck, we get even tighter constraints. And just to illustrate that, these black contours are our 2 sigma contours, or this is 1 sigma, this is 2 sigma. And here's Planck, here's WMAP. This may change in December, we don't know. And these are the Planck cluster constraints that were shown to be in tension with the Planck cosmology in all the earlier papers. We show that there's probably no tension. There may be errors here. There's no errors here. But so these are our combined constraints, which is great. They're about 1% constraints on sigma 8, which is nice. Now they could be better. Remember, I said that there's some systematic uncertainties in what this level is, what these measurements of the X-ray masses, the exact calibration of the X-ray masses. So what we did was we went out and we tried to measure these X-ray masses. So this is some new work that been led at CMU by Melanie Simett, myself, and Rachel Mandelbaum. And what we did was we took the RBC lensing sample, or as much as we could of the RBC lensing sample that overlapped with the Sloan shape catalog. And we went out and we measured, we had shear measurements and we cross-correlated with the shear measurements with the X-ray cluster positions. Some things we've included is we've included an offset in the modeling. So there's a lot going on here. So this is all the clusters stacked in one spot on the X-ray positions. So you take the shape catalogs, you have an X-ray position, you say, what does your weak lensing signal look like as a function of radius? This is if you split it into 2 mass bins, and this is if you split it into 4 mass bins. So low mass, medium mass, little higher mass, highest mass. You can see as you break it down, obviously it gets noisier. This is a very nice measurement. And so once you have this measurement, you have to then translate that into a mass. There's several ways to do that. You can fit it with an NFW. That's what we're showing here in blue. Or you can take simulations and say, well, what are simulations of comparable mass, or objects of comparable mass? You can then make weak lensing signals and interpolate. So I made a whole slew of weak lensing observations of clusters in different mass slots, and then you can fit or interpolate between different mass bins to try and nail down what the masses of this green, or what the masses of these red points by interpolating between bins.
So how many clusters were actually done?
This is about 186.
So if you develop the stack as opposed to showing the final state of the stack, do you see any anomalies relative to this brilliant NFW fit, associated with, for example, issues associated with alignment and other things? I mean, small number statistics will always give you those effects. Mm-hmm. And then this one's relying on somehow that the averaging is getting rid of it, but it's still got an anomaly associated with the, whether the lensing is on the line of sight or whether it's...
Right. So we included 0.5.
From the simulations you did. But
Yeah. No, the NFW fit also has an offset in it.
How did you do that?
I did not do that. Melanie did that, so I can ask her.
Blame it on her.
No. I'm not blaming it on her. She did it. It was great.
No, I mean, physically, how did it work? It was just... Did she actually take into account that it was an NFW plus other stuff?
No. She just offset the NFW by... so we're talking about offsets. So let's say that the X-ray center is not exactly the weak lensing center of your cluster.
This is done on a cluster by cluster basis.
Yeah, but that's a different question. That's
Okay.
the centering question. But the other question is well, as you know rather more than you'd like to, clusters are a messy business. And so a sphericalized NFW is not, even
Right.
if it's correctly
That's
centered,
not... So line of sight additions aren't taken into account in the NFW fit. They're in.
not, and
They're
so
in.
that's what's quite remarkable. But you don't see a deviation, and you're going out to 3 megaparsecs.
Yes. Well, I think the chi-squared is actually better for the simulations.
Well, but that's in short distances. I mean, they look pretty much the same.
I mean, if you look at the really large observations at Perseus, there's a tremendous amount of scattering,
That's
depending on which direction you go.
Yeah, exactly. So
Doesn't look NFW at all.
So a pretty interesting thing to do, and we've done this with the simulation, is because you have a sample of 100, you can do variance measures.
Sure.
I mean, I know that that's what those error bars are indicating, but I mean, real variance measures?
Well, I mean, we've done it on like a bin by bin sort of mass basis. But yeah, you know, you can't, the shape catalog, it's SDSS, that's the photometry for this catalog. So it's not like Subaru or anything like that's being done. So you don't actually, you only see a signal when you start stacking. You don't see a signal if you're not stacking. So that's why, you know, these two bins have about 27 clusters in each of them. Yeah, sorry, I think the total is about 160. So yeah, these are about 30, these are about 50. So you can see once you get down to small number statistics, the error bars really blow up. So I can't really say on an object by object basis how important line of sight.
But for each cluster, there is an effective, yes noisy, but an effective mass map that's being constructed, a kappa map, if you like. And then those are the things that are stacked. Now, it may be that that is a combined operation, so you only look at the, you know, the two things in combination of map and stack in order to get statistics up. But I'm just thinking of that neat thing that we did with the mirror on our great paper, where it showed the emergence of the cross-correlation in the stack. That was a pretty interesting thing to do.
I'll ask Melanie if she's done that.
Right?
Yeah.
And so it'd be interesting to, I mean, because after all, you have pretty good statistics. I mean, 100's not bad.
Yeah. Yeah, no, I'll ask Melanie if she's looked at, you know, building up an individual, you know, building up the individual signals to get the final signal. So, you know, like I said, we can fit to figure out what the weak lensing mass is, and we know what the X-ray mass is, or roughly what the effective X-ray mass is for each bin. So we can kind of get at what this bias is. So this large point here is that first bin. So this is the one, essentially the one bin stack. You can see we get about a 20% bias when you fit with the SIMs. These two larger points here are the two bin stack. And you can see they also fairly agree with, you know, this is obviously more significant, but you get about another, you know, 20%, 25%. Once you start breaking it down even more, you know, your error bars blow up a little bit, and you get this sort of, which we don't really understand yet, this sort of different bias as a function of mass.
The fact that they're scatters, the fact that there's such a shift between two very close mass bands.
Yeah, so this one's showing about, yeah, 70%.
Those two that are side by side. That one.
These two? What?
Have I misunderstood it?
This is every stack. This is all the clusters. This is the two
The
bins.
thing that's going through the 1.0 right there. I mean,
This is when we've broken it down into three, so there's a lot less clusters in here. This one contains all the clusters.
So I'm misinterpreting.
Yeah, so the weight of the symbol tells you about the bin and the binning that we've done.
So the NFW fit for the X-ray, cross-cutting X-ray, just see very on small.
No, we don't. No, there's an X-ray. That X-ray mass comes from that LXM scaling relation that they've calibrated, assuming hydrostatic equilibrium. So that's where we get the effective X-ray mass.
So you're doing simulations with feedback and finding a dark matter profile or a total mass profile which is less concentrated or shallower than NFW?
Not as peaky.
So less NFW.
Yeah. The total mass profile is less NFW. It's not. That's not surprising. I don't think that's surprising.
But the entropy looks just like NFW.
Yeah, that's just, yeah.
So another couple more interesting results with lensing. These two papers came out where people actually looked at cross-correlating lensing from the CMB or lensing from a weak lensing catalog with a Compton Y map. So this is a constructed map that's meant to remove the CMB and only has your Compton Y distortions in it. And these two papers came out one shortly after the other, and they, you know, they're showing that given the current state of the data, we can get about 6 sigma results in both of these, showing the cross correlation between. This is the CFHT lens survey and a Compton Y map constructed by this group here, and this is the Compton Y map cross correlated with a weak lensing map. A CMB lensing map. So they're probing different regions of space, but these signals are starting to come out. We already have a 6 sigma detection in each. The data is going to get better. So potential for higher sigma detections is coming up. So both these papers didn't use any sort of simulation to sort of model what they're seeing. I don't think they really need to at 6 sigma. They're really just getting a detection. But in the future, it'd be nice to see what these cross-correlation signals tell you. So what I'm showing you here is a comparison between an analytic calculation and the simulations. And the analytic's nice because you can break it down into your 1 halo and 2 halo term. And what's really nice is this cross-correlation signal. This is phi cross y, so phi is CMB phi. So this is CMB lensing cross-correlated with a Compton Y map. You get contributions, at least at low L, from the 2 halo term, which you don't get from the TC auto spectrum. This really tells you about what's the bias of pressurized gas in the universe. How does pressurized, how does your ionized gas trace the underlying dark matter? And out here, this is telling you about your gastrophysics. So what does your pressure profile look like? What does your overall mass profile look like? So what's really interesting here is this simulation doesn't assume any profiles, right? We just have the subgrid models that we throw in. This analytic calculation has the same pressure profile that we found in our simulation, so that we've calibrated off our simulation. So the only thing that's different between these two out here is the dark matter, or the underlying mass profile. So this deviation here is telling you about what the relative difference in the simulations, the profile in the simulations to the NFW profile, which is what they assumed when they calculated it. And so you can see as you go to higher L, the analytic theory is always higher. And that's, again, having to do with NFW profiles are peakier than what we're finding in the simulations. Therefore, you have to go much further in before you start resolving it. Whereas in the Compton Y, you don't. It cores out easier, so then you start losing your Poisson power much faster. This is plotted in funny units. This is L cubed CL.
Earlier talks you showed us you overpredicted. That was from your simulation. I heard a lot of you overpredicted.
In the auto spectrum, sure. Yeah.
So you're saying this helps a little bit.
No. I'm just saying these are interesting things that these cross-correlation measurements will start to probe. That's all I'm saying. If you can start disentangling what the pressure profile is doing, you can start making measurements of what the mass profile is doing. There are lots of caveats to this.
Have you tried to break it? So this, the analytics is done with a halo model, going down to what mass?
All masses.
So what does that mean, all mass?
10 to the 10.
So
It's assuming.
let me put it another way. So the halo model completely gets CL55,
The halo model is made sure.
not phi y,
Yeah.
phi phi.
The halo model, the check was made that it matched CL55.
So that means
Not observed CL55, just other previous theory calculations of CL.
theory calculations. In the simulations, the question I'm asking is, do you completely saturate CL55 by halos, or is there a significant effect outside of halos associated with the web?
You're talking about lensing from, say, filaments, or
Right.
there could be additional contributions there.
Well, you have the sims to
We are currently in the process of testing what CL, say, 5.5 from a lensing survey looks like compared to theory so for the same lensing survey, what does the theory calculation look like compared to the simulation calculation? And they appear to be agreeing right now. So,
But you have all the raw material within the simulations already.
right, so it's already in the simulation. So I'm saying that it looks like they agree. This is a very preliminary tentative statement. So in the halo calculation, including the second.
I don't care about the theory.
Okay.
You can do the cut so that you only include gravitational potential contributions from
We have mass cuts. We have done that.
objects, right? So
Yeah.
you can actually, so it's a numerical result that comes out immediately from the numerical simulations without anything associated with observations or with a theory.
So yeah, I do have those plots. They're not in this paper, and they're still. Oh, sorry, they're not in this presentation, but they're still tentative.
And you think that the halo model saturates it?
No, I didn't. I said I didn't say that. No, did not say that. Okay. Right. This is the halo calculation. We'll just skip through this pretty quickly. Like I said, it's also sensitive to, what your mass profile looks like. It's also sensitive to astrophysics, and it's also sensitive to cosmology. So these are all things that these cross correlations are going to probe. But there's going to be several of them, right? So I'm just showing you. This is CL phi y. This is phi gy. So this is now cross correlating with, say, something like CFHT lens. So you can see that the dependencies are different. You're also probing different halos of different masses at different redshifts. So let me just show you, the shapes do change when you go from CMB lensing to galaxy-galaxy lensing. And you're cross-correlating with Y. You get the same effect out here, different sort of biases going on here. But what this is really getting at, or what I'm really trying to get at, is when you start building up these different lensing surveys, you can start to do something like TSZ tomography with these cross correlations. And when you get several samples, when you have a CMB lens, that has a different mass and redshift distribution than a galaxy-galaxy lens. Galaxy-galaxy or galaxy-galaxy survey from, say, CFHT is different from HSC, is different from DES. So you can start to really break down the different contributions that go into these cross correlations and start to pull out certain aspects, certain mass ranges, certain redshifts, and really get at the underlying astrophysics and hopefully some of the underlying cosmology that's going on in these halos. I don't show it, but these cross correlations are probing halos of 10 to the 14, 10 to the 13 at higher redshifts around 0.5 and higher. That's right where observations of the TSZ auto spectrum are breaking down and where we have the most uncertainty. So, these future observations are definitely going to be an improvement on what we know about the astrophysics in clusters, low mass, high redshift halos. And these observations are going on, so let me just flash up some ACT-POL results. So this is just from our first year ACT-POL results. This is the TT observations, and these are our nice EE observations. And this is just one season with one detector tube. There's now 2 detector tubes in there, or 2 detector arrays. And we're taking more data right now. The 3rd detector will be deployed soon. So, this was very quick turnaround. This came out in the spring of this year, and we finished taking data at the end of 2013. So, these error bars will go down, by better than square root t. And we're getting nice high resolution, high signal to noise observations out in the tail. This is just ACT-POL going to advanced ACT. This is a new funded experiment. You can think of it as a CMB stage 3 experiment from the ground. It's funded. It's going to do a nice large area, about 20,000 square degrees. We're going to have multiple frequencies, so we can start doing things like what Planck did and start deconstructing the maps into the various different components. Because it's covering such a large area, there's several potentials for cross correlations. We will be covering the DS fields. We'll be covering all of the LSST fields, HSC. This is just some of the many fields that we'll be able to cross correlate with. So the potential for cross correlations is huge. I wrote down, just a quick calculation. It's going to be like n squared divided by 2. But so I won't keep you because it's already late. But some takeaways. I asked Dick what the conclusions should be. He said there are no conclusions, but I threw some up anyways. Every day, more and more CMB data is coming in. I know this because I'm actually observing sometimes with ACT. Improvements to the ICM model are necessary. I didn't really get into this, but if you want to talk to me about that, that'd be great. This is something, an area that I'm working in heavily right now. There is some mild tension in measurements of the TSE auto spectrum with the models. But there are ways around it. We don't necessarily have to just live with the auto spectrum. Cross correlations are great. We've already shown that they can be used to constrain cosmology fairly well. And we can also start getting at some of these gastrophysical questions that we want to know about. Thank you.
Well, I had one. So you use a linear bias in the two halo model,
That's correct.
right? B of M and Z. But given that you're correlating with clusters, is there some infall of the galaxies that are, of the matter that's doing the lensing around the clusters that's more nonlinear than a normal linear bias that you would expect in general on those?
You mean like contributions from, say, some sort of shear or?
Just infall
Okay.
around these large, the clusters that you're correlating with.
Well, so there are, if you look at in the area where the bias dominates the two halo term, there are differences between what we're seeing in the simulations and what we're seeing in the halo calculations. That could be one contributing factor to that difference. That's something that we probably have to look into a little bit more.